So lakes that are quite big, you go to with a truck, you can get a boat out, you can row around on the boat, and you can measure the depth. That's okay, that's not bad. The challenge is when you've got smaller lakes that are probably high up in the mountain, more difficult to get to. How do you work out the volume of that? It's more tricky. So we were building small surface vessels that you can put into a backpack, climb a mountain on foot, stick it in the lake, and then measure the volume of that lake, and that's the idea. We're working in this Khumbu area of Nepal here, trying to map these lakes on here. So we built quite a small, simple boat. Actually, this was done by our level 4 undergraduate students. So, they're still learning their trade effectively, but they did an amazing thing with this particular project. So it comes in 3 sections, goes into your backpack. It looks a bit kind of clunky. We have these big bolts on here, this big hook. Bear in mind here though, when you deploy your robot, it's cold. You're wearing thick gloves. You don't want to be able to have screwdrivers, things that fall apart. You want to be able to do it with thick gloves on. So we have big bolts, big pins, so you can pull the pin out, you can unbolt it, put it in your backpack really, really easily. So you see here, beautiful, beautiful place in Nepal. It's a lovely place to be. Right down here is our little robot here. This is one of the bigger lakes, one of our testing lakes here. We'll zoom in. We'll zoom in, you'll see it down here, give you more context of what it is in the lake down there. If you ever wondered what it would like to be on a glacial melt lake, I can show you a video from the top of our boat. So we go on here, it's quite flat, quite smooth, but there is some things falling down here. You see these things here. So even if you could get on there with a boat, it could be quite dangerous. So it's the challenge of getting there, but also the dangers, the risks of doing it are potentially quite high as well. So you can see here, beautiful, beautiful place. And to give you some idea of scale, these are the guys here who are watching it who are doing the testing. So this is one of the bigger lakes in the pool we're working in. So yeah, beautiful thing. So the way we do this is kind of a semi-autonomous kind of way. I mentioned at the beginning, it's very hard to use things like robot vision to work out what things are. So it'd be really hard to put the boat into the lake and say, just go and map it. That's really hard to do. So what we do is, a person, a human, manually drives around the outside of the lake. That defines the boundary. Then you press go. In this case, it's trying to do a spiral search. So as it drives around, it does sonar sensor measurements. So it's pinging sound down to the bottom of the lake and measuring the sound coming back. Like I showed you before with the actual room thing, sound goes down, you measure it coming back, you measure how deep it is at that point. So it's trying to do a spiral search going around to kind of get points across the entire lake. You can see here, not perfect. There is some kind of errors there. This is to do with kind of wind and water. It's quite hard to track, but that's fine. We don't need it to be perfect. We just need a good number of points around the lake, which is important. You can convert these points into a surface map here. That gives you the idea of the surface or the volume, and of course the volume is very important. So let's look at the results of this. So these blue dots here were the data taken by people with trucks and with boats. So you have this side here is volume, the volume of the lake. This side here is area. So the blue dots, they really land quite nicely on a straight line. Our data is the red dots, the smaller lakes, and the really great result here is, in fact, they line up. What you want. So from this, we have a really good understanding about the surface area and the volume. So now they can use satellite images at any time of the year. From that, work out the volume and therefore know about global warming. So it's a really big result. So an undergraduate student project, a good international journal from this output. So it's a good example of okay, what you can do with relatively simple technology, but in the right application area. So that's the surface things. Of course, open spaces are great to fly in, to fly around. So we've been working on that sort of thing as well. How can you fly around to do exploration type tasks? So I'm going to show you a drone now. So we have drones that fly around, of course. The good thing about drones is they are very stable, very reliable. As before, the bad thing is actually the energy is quite difficult. So in this case, I'm going to show you now is what you call a marsupial robot, like a kangaroo. It's a robot that carries another robot. So you go somewhere, you deploy the robot, and then you have two robots that can do things. Let's see what happens here. not the most smart robot, it can't see that leg, but anyway, it does mostly what it should do. One of our big drones, about 1 metre or so across, it's very, very big. I really don't get the scale, but it's actually really scary. If you're near it, you really feel that power and that energy. It can carry about 10 kilograms. It's a really big drone. And now, so we drop the little vehicle, the big one goes away, and now the big one can go and do the scanning by itself. So it goes away and just scans. This is actually a power station that's scanning right now. Go away and start to map it in that area. As well as that, we also use our drones to deposit material. So sometimes you want to add some material to something, maybe some kind of leak. So we have drones that can fly with printers on. In this case, it's a conventional plastic printer. You can fly somewhere, you can land, and you can deposit material to repair something. Like I said before, this is plastic. We can do the same things in different kind of structural materials, such as tarmac type materials or other resins that are very strong that can repair things. So it's quite a nice, useful technology we're developing for repairing things. So to mention drones, as I've said kind of several times now, drones or rotary drones aren't great with their power consumption. So it's fine, go somewhere, half an hour, come back, that's okay. If you want to be having a survey of a field for several days, several weeks, you really need a more conventional plane. I guess a fixed wing type aircraft is what you need to have. The problem with fixed wing aircraft, I'll show you now, especially if they're quite large ones, they really require runways and they require landing things. So you launch them and land them from runways. So the state of the art right now in launching large-ish, large airplanes is like this. So we're going to see a video now. This is a kind of fairly large vehicle. I guess it's 2 meters across. The state of the art launch and recovery of one of these vehicles I'll show you now. So it drives on a truck, gets some good airspeed. It can take off. That's quite nice. It flies around. And of course you want to recover it, so when it's finished its day-long survey, how do you get it back? So you throw a parachute out, check out a parachute, and it lands. It works okay if you're in a field somewhere, and you can do that, but it still requires somebody to go and collect it, and of course it might, in an urban centre, you just can't do that, you'll hurt somebody. So you need a method of being able to land larger UAVs at a particular point that's not very big. So a runway would be fine, but it's not very big. So there are other approaches. This approach here is for smaller vehicles, you can have humans that can catch them. This person here I don't know, it's from a video from YouTube. You can see here he's trying to learn to catch these things. But it's difficult, he's not that great actually, to be fair, he's not good at catching it. It's quite hard to catch, to be fair to him. But it comes in, you've got to cut the speed down of the UAV, you've got to try to catch it. It's difficult, he gets better as it goes along, but it's difficult. So the question is, could we try and do this for larger air vehicles? We're working a lot actually at Leeds on that right now, so we don't have the answer. I'll tell you some of the problems, some of the solutions. We don't have the answers for the full solution right now, but we're pretty sure we can catch air vehicles up to 5 meters in wingspan with a very simple kind of mechanism, which would be really amazing. So the problem is though, you've got an air vehicle, you want to catch it. Imagine a cricket ball. Someone throws a ball at you, you want to catch it. Think about how you catch that. So you put your arms out, you estimate its speed, you have to kind of touch it gently, then you pull it towards yourself, and over that period of time you take the energy out. So it's quite a complicated thing to do this. If you do it wrong, you hurt your hands, you drop the ball, these things go wrong. So you need to get it right. In this kind of context, if you have a vehicle or a robot that can try and catch a plane going quite fast, if you get it wrong, you break the air vehicle or you break the capture thing. So you could fly it very fast at a thing called a spring damper. Effectively, a spring is something, of course, you apply a force. As you get more and more compressed, it applies more force. A damper, like a big kind of, I guess a bicycle pump, you push it. The harder you push it, the harder it feels. So you can get this kind of thing here. And what you find is you get this kind of spike. So this is a thing called jerk. So maybe you haven't heard of what jerk is. So I guess you know about position. You can differentiate position to get velocity, the speed. You can go from velocity to acceleration, how fast it's going. The next one is actually jerk. So the differential of acceleration is jerk. And jerk is a very good measure of the shock in a system. So if an aircraft's going to brake, you want to minimize the jerk. Jerk means structural failure on many joints. So we don't want spikes of jerk. Spikes of jerk are very bad. So we've developed algorithms, and this is a graph here of the kind of, this side here is the force against distance. So again, cricket ball's coming towards you. Initially, this is the point where your hand touches the ball. You are passing no force between your hands and the ball. As the ball comes towards you, distance here, you increase that force, bearing in mind the force is slowing the ball down. At some point though, the ball's getting slower, you then reduce the amount of force. You're still carrying going, reduce the amount of force, and at this point here, of course, you've got no force applied. The ball stopped, you're holding it, and you stopped. We want to put this onto a robot, and of course, this shape depends upon how fast the aircraft's going and how heavy it is. So if I throw to you a cricket ball, you catch it. If I throw a ball that looks like a cricket ball, but is actually much lighter, you would do the same thing, but the moment you touch it, it would feel different, and you'd do a bad catch. So this shape is really dependent upon the speed and the force of things. So for an aircraft, it's the same thing. We need to know how heavy it is, how fast it is, and it's very hard to know the speed in particular. So again, if someone throws a ball at you, you might say, throw it to me at 2 meters a second. When you catch it, it'll be different. So not only do you want to have this shape of force, it must be able to adjust. So the moment you touch that, as your brain does, you change what you're doing. You change the shape of this graph, and that helps you to catch it. So for the jerk here, you see this kind of shape. There is jerk, there is change in acceleration, but it's smooth. There are no massive spikes, therefore the structure you're going to catch shouldn't break, hopefully. So here's a simulation we've been doing. I won't run the thing here, but simulation, a robot arm, an object's coming. The question is though, we don't know how heavy it is, we don't know how fast it's going. Really important parameters for the energy. So we have things, so as you catch it, you can adjust what you're doing. Here's an example of some simulation of the mass. We thought it was 4 kilograms. As we touch it here, we can rapidly retune and we can measure. So as you catch it, you know how fast it's going, you know what you're doing, so you can measure and you can change these things. Likewise, this curve of force against displacement. Originally, we were going to apply that. The moment we caught it, we worked out, hang on a minute, it's going at a different speed, not as heavy as we thought. We automatically retune this, like you can see here, and you end up with the blue line here. Similar, not quite the same, but still has low jerk, still has low thing, which is good. We've got a little video here of another part of it. So we mentioned about the point where you catch it, but we care also about the initial point. So you have to initially be able to get your thing to be no contact force. So as the vehicle, in this case it's a small car, as it approaches, you want to minimize this contact force here, otherwise it will bounce off. As you do with the ball, you catch your hand. So what you'll see here is that in the next video, we've got the cart going over a box here. The speed is different, so we automatically retune this. You can see here the graph here, we're automatically retuning. This is the point of contact here. So here, so you can see here there's no contact force, they synchronize here, and then this is where you apply that bell-shaped curve. It's quite squashed here, it's a bell-shaped curve. So in contact, you change the force, but also to make sure that that initial contact point is no force. You get the speeds aligned, you get no force. So I've covered now things to do with open spaces. There are other spaces that are also quite important to cover. So very importantly, confined spaces. Confined spaces being things that are restricted, they're small, you have to build small robots in these spaces. For example, sewage pipes and air conditioning systems. And people often say to me, okay, well, you're into robotics, what is going to be the first most useful robot that ever could be made? And they expect me to say things like, it's going to be a humanoid robot, maybe an autonomous car. For me, again, the best business case, the business case being the thing that makes the most financial sense, the most environmental sense, is robots in these spaces. The reasons is that technically they are simpler, there are no people, they're defined, simpler spaces, less risk involved. but also in terms of the actual impact. So financially it's important, but environmentally, if a pipe underground has a leak, you dig a big hole. The big hole causes traffic delays, causes fumes, pollution, cost. You're late for work, you've lost a job, you've lost things. So the financial and environmental quality of robots and pipes is huge, massive thing. So if I was starting out right now, if I was in your shoes and I wanted to do robotics, I'd be thinking, I'm going to build a robot that's going to be the best robot ever in pipes. And I think if you could do it right, you'd make a lot of money. And I know for a fact that many companies come to me and they want to buy them. They don't want to make them. They don't want to give me money to make one. They say to me, well, I'm not going to give you money. If you can sell me one, I'll buy one. So there's definitely opportunity there, I think, in that area. Not for me, I don't think, but for maybe for you guys. So I'll tell you about one of the examples of working in confined spaces. It's not in city environments, not in kind of that. It's a very specialised case. It's our work on the Great Pyramid of Giza. But effectively, we're driving around in a square environment, square tube. So I'll show you the pyramid here. Beautiful, amazing structure in Egypt. Really, really stunning. If you were able to cut it in half, it would be great. You'd see amazing things, no doubt. But the things you would see we know about are these things here. You have a queen's chamber and a king's chamber. And you have these, what they call air shafts. The top ones go to the outside, which is why it's called an air shaft. But very importantly, the ones in the queen's chamber here, they don't leave the pyramid. So what we're trying to find out is, well, why would you build a shaft in the pyramid? Bear in mind, you've got to cut it into stone. It's very hard to do. In fact, you don't cut it into stone. You design the stone blocks before you assemble it in this context. Very, very hard to do. So what are the shafts for? Where do they go? And where do they lead to? So you can see here in more detail the king's chamber shafts, why they're called air shafts. They leave the pyramid. For the queen's chamber, though, there's this thing here. It could be 20 tons of rock, or it could be a hidden chamber. Nobody knows. That's what we're trying to find out. So there's a square tunnel here, goes flat for a little bit, and then goes up at an angle of 40 degrees up towards the actual the end point of the shaft. So it sounds quite simple. When this job came to me, I was like, okay, yeah, I can do that. I'll get a radio-controlled car, I'll modify it a little bit. How hard can it be? Just get up there and things. 7 years later, we're still building the robot, and finally we're successful. So I think it's a good example of perseverance. And I guess another thing I'd say to you, when this came to me, there was no money attached to it. So it was very hard. Well, it was a decision about, do I want to do it really? Do I want to kind of, even though there's no money attached to it, they're not going to pay me, do I want to really make it happen? So after many years of doing it, I guess in spare time, that kind of thing, with a team of people also doing it in spare time, we achieved a solution. So don't be put off doing amazing things because it's somehow hard financially. I think amazing things are worthwhile doing for many, many reasons. So anyway, you're in the shafts here. The shafts are mostly beautiful, square, clean shafts. But there are things that are moving, things that are changing. So here you've got the block that moves sideways. Here you've got a floor block that's moved down. So subtle things, but for a robot to drive in the shaft, they're really, really important. And in particular here, of course, bear in mind that these look like they're flat, but the photographs are taken along the shaft, but the shaft is going up. So you've got to climb a shaft like a rock climber and get around the block. Or if you're going to drive up here, how do you get over that stone? It's on the floor. It's going to make it harder to drive over it. So how can you do that? So what we were trying to do, a previous team had been there. They'd driven the shaft. They'd found a space here. They didn't know what the space was. They put a camera through. They saw nothing. So our mission was to try and explore this first space here, which we did, which I'll show you in a second. And the second question was, can we drill this block here? We didn't do that yet, so that's still work in progress. But we can tell you what we found in this space here, which was our result from this project. Quite interesting. So the challenge is, though, you're climbing in a shaft here. You can't just put a radio-controlled car in there and drive up. You just can't do it. You have to have what you call a reaction force. So you have to push down. If you try and drive, your wheels slip, they spin. You just can't do it. So how can you do that? So we worked a lot on this sort of thing here, trying to build different vehicles, so different designs of things. But the important thing is you've got to apply a reaction force, but you have a cable. You have to pull not only the weight of the robot, but also the weight of the cable. We have a cable because we want to guarantee we can get power to it, and also pull it out. If you get this wrong, you spend the rest of your career building rescue robots to remove the robot that you've got damaged. So you really don't want that. You want to get it in safely, and get it out. So it's a real big challenge to do that. So what we used was the inchworm locomotion. Little animal. The way it works is the front bit grips, the middle bit flexes, and the back bit grips. So 2 points of gripping, and they move together. Amazing little creatures. So how can you walk around? How can you move around in this environment? So of course we didn't build inchworms like this, but we were inspired by the approach to build different kinds of robots. So our inchworm robot, not quite as nice and organic as that, but works the same principles. We have these pads. This is a shaft. These panels here are a shaft. We have pads that push out, so grip sideways in the shaft. One's at the front, one's at the back. We also have a carriage here that can drive forward and backwards. So this carriage forward and backwards is like the little bug bending its belly. And these things here are like the teeth gripping in. So you see here a sequence of motion. So we pull them in, we push it back, we grip here, we release there, we push backwards. This one's going backwards, but you get the idea. It's gripping and releasing. The really good thing about this is there is no scraping. So you get a tank truck in there, it's going to scratch away at the surface. That's really, really bad. We don't want that. We want gentle, soft things in that environment. Here's a robot here. So it has 15 different cameras. So what you find is in the pyramid, very quickly, it's very stressful. It may as well be on a different planet. You put it in the stone, once it's beyond arm reach, that's it. You ain't going to get it out. So you want cameras to see what's going on. We have lots of 3D printed plastic material on here. People often also say to me, okay, this one in plastic's great, where's the real one? Show me the big metal one with massive bits of metal on. But of course, because you're climbing, it's really an aerospace type problem. You want it to be as light as possible, so the more weight it is, the harder you have to grip. So it's like climbing a building. You're carrying very heavy weights on your back, you've got to push harder, you've got to work harder. The best possible robot would be a cardboard robot. If it's cardboard, it would be beautiful, it would be light, it would be simple. That's what we want. We don't want anything heavy. So plastic, very simple plastic. Where you want things that are strong, you have them strong, but mostly it's very gentle, very soft, very light. That's what we want. So you can see here the shaft again. People often say to me also, why have you got a big front wheel? I showed you before the step. The big front wheel makes it easier to drive over that step. So as you know in a car, the bigger wheels in the car, the easier it is to climb things. So a big front wheel, once you're over the step, it's easier to pull your back wheel across. So that's why we have these two different sizes of wheels on the vehicle. So built through a metal spine here, so this is the bit that does the work. This bit goes forward and backwards, that does the pulling motion climbing up. On the same spine we have drills. These drills extend forward and we can put tools, drills, cameras, that kind of thing on the robot. Add some plastic to it, like this. So these wheels, by the way, these wheels do not do any driving. They're not like a car wheel driven around. They just stop the belly from scratching along the floor. So the wheels are like free to spin, and it just gradually supports its way up the pyramid. Built custom drills. You see here the drilling problem. So ideally, we want to drill the second stone. To drill the second stone, you have to reach through the first stone and drill up here. But we can do that, we can do that. And notice here, I guess the subtlety here is, the good thing about the angle is it makes it easier. The dust falls out. Dust falling out is good, because if dust stays in there, it gets clogged together, that's really bad. So dust falling out is really good, makes it simple. So you can see here also we have a snake camera. So this camera is designed to go through the hole and designed to look around in that space and understand what's in there. So I mentioned before, the previous team put a camera straight through. They saw nothing. We want to really explore that small space. Quite a small space, but what's there? Where does it go to? Nobody knew, so we wanted to go and find out the answers to this. You can see us here, you see Adrian, who's at the front here, working hard deploying the robots, and we're obviously working on computers. So this is in the pyramid itself, we're doing this. So as before, when the robot's gone, it might as well be in space. So once it's got inside there, you have no way of reaching it. It's just gone forever if you can't get it out again. You see here again it being deployed, you get the idea of the scale of it being deployed in the pyramid itself. So as you climb the shaft, you see some features of the shaft. So you see some detail here of different things. This red line here, by the way, is a builder's mark. So when they built the pyramid, they used red paint to line out what they were going to cut. That's a marker there, and then of course they cut out the stone with that red paint, and because the block's moved, you can see the original marker, again done thousands of years ago. So 3,000 or 4,000 years ago, somebody drew that, they carved around it, and you can see in this thing here. So you'll see it's actually walking now. So it works like an inter-moment locomotion mechanism. You have the front ones that brace, back ones that brace, and it gets forward and gets bigger and smaller. We're getting towards the end of the shaft here. This is the very end of the blocking stone we're trying to explore. The cameras automatically are changing, the lights are changing, so you can see what's going on here. So if you don't change the lights, you look at a light, you just see the light. So it's very important both the cameras and the lights change in the shaft itself. You can see here, at this point our overriding thought is, do not touch that end stone. You touch the end stone, you might damage it, but also you might fall down. You really don't want to fall down. So right now we're getting quite nervous about, let's not hit the end stone, let's make sure we're safe with it. You can see here we're getting quite close to the end stone. But as you get towards the end, the stone is much better, much purer white Tura limestone, beautiful stone, towards the end of the shaft. So as we got there, we got to the shaft. The first question really we're trying to answer is, we know the shaft ends in a blocking stone. Has that been carved in, or has it been dropped in? And you can see here you have a small ledge. Nobody's seen it before. The bottom here is a small ledge. That's what you do normally when you want to put things inside things. So that really implies the block has been dropped in. So this block is not part of a carved stone, it's being dropped into place, into the channel. That's quite an interesting result by itself. You'll see these things here, these are copper pins. They occur nowhere else in Egypt. Nobody knows what they're for. But the main question here is, how are they attached? Nobody knew. Are they glued on the front? Do they go through the stone? So we're trying to answer these questions of the thing. So you see here, this is the previous hole drilled by our previous team. So we're now going to deploy our camera through the hole. At this point, again, very stressful. Will it line up? Can we get there? Can we see what's going on? So it's kind of a time-lapse thing. It wasn't this fast, it was slower than this. You can see it going in the shaft there. So obviously quite a stressful moment. So at this point here, we got a glimpse of it, and then what happened was, in Egypt they said, that's it, turn it all off, we want to get our boss to come and see it. So we had to go home, even though I could press one button and I could find out the answer. I had to go home to the hotel, wait all night, and go back the following morning when the boss came to see what was going on. So it's quite an interesting night, thinking what could be there, we don't know. Nothing or something, we just didn't know. Anyway, I had a good result. So what we found was that the actual bottom looking down was covered in writing. This writing has never been seen for 4,000 years. So since they built the pyramid, it was sealed. Nobody had ever seen this apart from us. It was the first time we were seeing this ever since that point. Writing, some of it covered by dust, hard to read, but little writing, but adding to the mystery. It didn't really give us answers. Possibly saying 21. 21 sounds quite dull. Why is that important? But 21 is very important spiritually in Egypt. So if it's 21, it means it's to do with the actual length, which means it's to do with maybe a spiritual reason. So they've done it for good luck at certain lengths. So it could be spiritual. We think it is probably spiritual. It's quite a nice result. Also, we put our snake camera through. I mentioned a minute ago, we wanted to understand how are these pins attached to the stone. You look through, you look back on yourself. This is the outside, this is the inside. You see it curves in these very small curves around the stone. And inside here is a small hole, but it's only about 3 or 4 millimeters. So it's not big enough to use as a rope to lower it down, it wouldn't be strong enough. So that gives us the answer that it is actually a spiritual reason for that. So we've got some great results on this. What we haven't done, of course, is we haven't answered the main question, I guess the most exciting question, what's going on here? So we are in discussion with Egypt right now. We're hoping to get back at some point, of course. It's been quite a difficult time the last few years in Egypt, but hopefully at some point we'll get back and finally answer that question. But certainly, I haven't got the video to show you now, we did a full scan of this surface here, and there are some interesting things on that surface that indicate there could be something nice there, so we'll see. So hopefully, at some point we'll go back and we'll find the final answer We have the technology now to go there, to drill, to measure, so hopefully we can get there and do that kind of thing quite soon. That's our most famous one. We're talking about, go back to the beginning where I started this, I guess. We're talking about exploring pipes. The same technology could be used to explore in actual pipes in cities, that kind of thing. We also have more advanced things we're doing. So we're doing work exploring very large, 1 meter-like diameter pipes. In this case here, it's a gas distribution centre. So gas in the UK, it comes to one point, they have huge turbine blades, actually jet engines they have, and they fire the gas across the country from these points. So they're really, really important. They were put in about 50 years ago. Every 50 years they're due for renewal at a cost of 50 million UK pounds. Right now nobody can inspect them because they're too complicated. They bend, you see here all these kind of bends, they can't inspect them. So they have to replace them. If we can inspect them, and if we can say they're good, we can save 50 million pounds. Say, okay, well, let's just change them in 20 years' time, 30 years' time. Nobody knows, so we're hoping to be able to find the answer in the future.